In the previous video, we described how the combination of isoprenes can help us to create greater molecules that we call terpenes. We also described how the molecule of isoprene itself is not the one that is going to be useful, but the two isoprene equivalents with the pyrophosphate. And we are going to also learn how to synthesize these two substances by using units of acetyl coenzyme A. In this reaction, we are first going to combine 2 units of acetyl coenzyme A. We're going to add a third molecule of acetyl coenzyme A. So the first reaction will be a condensation reaction, and that's going to be a Claisen condensation for the first step. On the second step, we add 1 more acetyl coenzyme A, and that will be an aldol condensation reaction. So we have two different kind of condensation reactions. On the third step, we're going to do a hydrolysis of a thioester bond, which is nearly identical to a hydrolysis of a regular ester. If you do a hydrolysis of an ester, you produce a carboxylic acid and an alcohol. In this case, upon hydrolysis, we are going to generate a carboxylic acid and a thiol, and that is actually the molecule of acetyl coenzyme A. Then after we do the hydrolysis, we're going to do the reduction of a thioester. When we do the reduction of an ester using lithium aluminum hydride, we will get a primary alcohol. So the molecule end product will have a carboxylic acid end and also will have a primary alcohol. So let's start the mechanism of the reaction. I have done the drawing of the molecules to save the time for the uploading in YouTube. That is going to help me. So the first step of the mechanism is the use of a base. Since this is using biological systems, we need to remember that probably will be an amino acid side chain of an enzyme. And in that reaction, we have the abstraction of an alpha hydrogen. So you have 2 units of acetyl coenzyme A. That is the first description. We say first, step number 1, 2 units of acetyl coenzyme A react using a Claisen. And in a Claisen, you react 2 esters. In this case, it's 2 different thioesters. So we're going to create an enolate. So we're going to make an enolate because we're now combining that, producing BH. Now we have removed this hydrogen. Now this set of 2 electrons that we have left over, we can actually go and do the enol, but in this case, we're going to save time. Let's say that these 2 electrons will be the one because we're doing a Claisen condensation. And if we look at, we have a carbonyl that have a partial negative charge on the oxygen and a partial plus charge. So this is an excellent. This enolate is going to be an excellent nucleophile to attack the carbonyl. We're going to produce an intermediate that we always say that is a tetrahedral. So you see, following the colors, we added the alpha carbon of 1 unit of acetyl coenzyme A to the carbonyl, and that will, when we do this, when you add, you're going to open up this bond. We have a negative charge, but in the family of derivatives of carboxylic acids, we always will say that the carbonyl is going to reform. So we are going to reform the carbonyl, and we are going to have that, we're going to release a unit of coenzyme A. So coenzyme A that has a free thiol group, and that's what we're going to represent in here. So that's going to be protonated by either base, H, or it's just a proton transfer. And the product of a Claisen, we remember that the product of a Claisen is a beta keto ester. So that is, this is the alpha carbon, this is the beta carbon. If we do the redrawing of the molecule, which I have on the next page, but why not? If I still can do it, let's do it. So we have, this is the 2 carbons of the first unit of acetyl CoA, and then the second 2 carbons of the second unit of acetyl coenzyme A. And we'll now have only 1 unit of coenzyme 8 attached, making a thioester. So there is a beta-keto thioester. On the second step, if we go back and read, we need to add a third unit of acetyl-CoA. So we have a third unit of acetyl coenzyme A to gonna be added to the beta-keto ester, and in that reaction will be an aldol condensation reaction. So if it is an aldol condensation reaction, you do an addition and you do not reform the carbonyl. So we're gonna do the same. We're gonna remove the proton from the alpha carbon. That is going to generate an enolate, like in the chalcone synthesis. Now these two electrons are going to attack to the ketone because it is an aldol condensation reaction. And now we're gonna open this up. And if you guys follow that, this is going to be protonated. So we get VH, but at the end, I'm going to have a proton. Remember that this is using enzymes. So we are from that second step. So you add these two electrons from the alpha carbon to the carbonyl. That is the beta ketone group. And that will be an aldol condensation reaction. We are not reforming the carbonyl. And we are now adding, we still have this metal. Let me put a CH3 here to make sure that we remember where is that at. It's the same one. Let me give it the same green color so we don't lose it. And now this, I will do two steps. The first step will be a hydrolysis, and when I do the hydrolysis, I'm going to break apart the thioester. Remember that this is enzymatic catalysis. So you have two different acetyl-CoA sides, but the enzyme recognizes this side. It's actually symmetric. 1, 2, 3, 1, 2, 3. It's symmetric. So one of the two is going to be hydrolyzed. So we do hydrolysis, and then we get the carboxylate. I put the hydrogen, then I remember no hydrogen because this is in enzymatic catalysis and a physiological pH. We will have the negative charge. Remember that this is not happening only in plants, but it's also happening in animals. And then we have, that's the product of the hydrolysis. So let's put the word hydrolysis for this part. And then we're going to need to reduce. If you do reduction, let me remind you that in a small box, if you do a reduction of an ester, this is reviewing, we use lithium, aluminum hydride 4. And if you do that using that strong reducing agent, you get a primary alcohol on one side and another primary alcohol on the other side. So you get two primary alcohols. But in our case, we are getting one primary alcohol, and on the other side, so let me just highlight on green, we are not using lithium aluminum hydride. We are using a reducing agent found in biological systems, that is NADPH. So if we use a reducing agent that is too strong, it might reduce also the carboxylate group, but we don't want to reduce both of them. We're going to reduce only one of them. So this is a very mild reducing agent that is going to reduce only the thioester. Remember, as the reaction of esters you can reduce. And the second product, we need to use 2 moles of that because we are reducing the ester, the carbonyl, but also we need to provide a hydrogen to produce back coenzyme A. So we are getting 2 hydrogens out the reducing agent. So this is 1 and 2. And we are producing as a byproduct 2 NADP plus. Like we have discussed before, NAD plus as coenzymes for for reduction reactions, we use NADPH, and NADP plus is the byproduct. When we use in metabolism NADPH, this is actually for electron transfer, electron acceptor. This is an electron acceptor that is taken as a hydride. But in our case, for reduction, we use NADP. plus pH. All right. Then after we have that done, now how does the mevalonate becomes the pyrophosphate unit that we need to have? The first thing is we're going to have two consecutive phosphorylations. So the unit of mevalonate to become isoprene pyrophosphate. Let me put the word isoprene pyrophosphate. This is what we want to do. To become isoprene pyrophosphate, the first thing is we need to have two phosphorylations. So this is mevalonate that needs to become isoprene pyrophosphate. So the first step is two phosphorylation. This is consecutive. It's using 2 units of ATP. So you are getting 2 ADPs and 1 phosphate unit given at a time. So the first unit, you get to this point. Second unit, you get another phosphoryl group. And then the third unit of the phosphate will be given to the tertiary alcohol that we have on the beta carbon. So this is the alpha carbon, the beta carbon. So we are going to do a third phosphorylation. First phosphorylation is taking place on the primary alcohol. Second phosphorylation is on the to make a phosphoanhydride. So the second phosphorylation makes a phosphoanhydride, which is actually good because that's now an activated isoprene that can increase in carbons. So now we have 3 phosphate units in the unit of mevalonate. Mevalonate now has 1, 2, actually here, 1, 2, 3 units. 1, 2, 3 units of phosphate. So in order for to obtain the one that we need, because this one has 6 carbons, and we only need 5 carbons, we need to have a decarboxylation. So after, that's the purpose of actually the third phosphorylation, is to create a carbocation, a tertiary carbocation that is rather very stable carbocation. So by losing a unit of the inorganic phosphate, that we call that orthophosphate, phosphate is another name for that. We generate a carbocation that is very stable. So when we are losing, because we are now going to form a molecule of carbon dioxide, now these 2 electrons that are left behind are going to create the double bond, and that is going to suffice the octet for that carbon, and that is the unit of what I call IPP. What is that? IPP. It stands for isoprene pyrophosphate. Isoprene pyrophosphate. Now, how are those 2 units of isoprene pyrophosphate and dimethyl allyl pyrophosphate are going to combine? The first thing is you have isopentyl pyrophosphate that I call, or isoprene pyrophosphate. This one will have a chemical reaction of an SN2 mechanism. That will be an SN2 mechanism. It will actually be an alkylation. This is an alkylation using an SN2 mechanism, because now the pyrophosphate is an excellent leaving group. So we're going to create a brand new bond between one unit that has 5 carbons, and the second one will release pyrophosphate. Once we have done that, after the addition, we are going to remove one of the hydrogens using a molecule of water. When that is released, now we are going to create the double bond. And in this example alone, we have seen the synthesis of geraniol. This is the synthesis of geraniol. But as a matter of fact, if we continue using just this compound, this alone, because now we have 10 carbons, this is a 10 carbons, that molecule of 10 carbons can be used, let's see, to make, we have seen up to this point when we have 2 units combined. That was what I just discussed in the previous page. This one was discussed in the previous page, all right? But these two can continue increasing in number of carbons by adding some more. We exactly the same mechanism. So we go from having not a joint of 2 carbon units, we have done that. One of them is an excellent leaving group. Then you have one more that can also continue increasing. That will be a leaving group, and you bring one more until we make farnesyl. Once we have made 2 farnesyls, farnesyls are going to combine as well to make squalene. This is one farnesyl and a second farnesyl. Same mechanism of reaction, so you're going to add them up to produce squalene, which is the substance that we need to make cholesterol. And we have to make another video for cholesterol.